In this lecture, we will start single variable optimization. First, the basic concepts. A point x star is known as a local minimum of function fx, local minimum or relative minimum of function fx if the formal definition, mathematical definition is like this: if there exists an epsilon understood to be very small such that f of x star, that is the function value at the current point, is less than equal to all the other neighboring function values in this neighborhood. Okay, so for all x in an interval with x star at the center and plus minus epsilon on both sides. That means that it is a local minimum point if all the other values in the local neighborhood are no better. Okay, because it is less than equal to. So then it is a local minimum point. Now, the idea is that if we are calling a particular point as a minimum point, then we expect the function values at neighboring points to be higher. But equal will do. That is the sense. Okay. And why there exists an epsilon? Because the idea is that you tell whatever tolerance you want, and within that we will get the situation that all other points are either worse, that is higher, or equal. Okay. Now there are a few obvious extensions of this in certain situations. For example, if the function domain ends at x star, then either this side will not be there in the domain or that side will not be domain in the domain. Okay. So if x star happens to be an extreme point of the feasible domain of the function, then the interval of comparison will be one-sided. So, for example, if it happens that x star happens to be the lower limit of the domain, okay, then for this to be minimum point, you cannot say that we do not have this. Okay, so for this to be a minimum point, it is enough that on the right side, all other points are equal or worse. Similarly, if x star happens to be the uppermost point of the domain, then on this side it will close. Okay, so this is for the extreme points of the domain sitting as x star. And if it happens that fx star is less than fx for all other x, okay, so in this interval, whatever other x you find, if everywhere the function value is higher, not equal to this anywhere, okay, then you say that it is a strict local minimum. Okay, so if the strict inequality holds, then you will call it a strict local minimum. Now, if this can be true for all epsilon, that is larger, still larger, still larger, still larger, and so on, if it is valid, if this condition is valid for all epsilon, then that means that, I mean, epsilon doesn't have to be small anymore. Then you say that it is a global minimum. Okay. And similarly, strict global minimum if complete domain can sit here with epsilon with strict inequality. Then you will say strict global minimum. Okay. Now, all these definitions will work exactly valid if you reverse the inequality and make it maximum. Okay. So whatever holds for minimum, similar things will hold for maximum with the inequality reversed. Okay. Now that is why we do not need to separately study maximization. We just study minimization, and if maximization happens to be the task, then we minimize the negative of the objective function. Okay. Maxima and minima together are known as extrema, extreme values. Okay. So extremum can be a minimum or a maximum. Now, in mathematics, there are two terms which are close by. Do not get confused with them. Okay. One is infimum, which is close to minimum, and another is supremum, which is close to maximum. Infimum is known as greatest lower bound. That is, for a function, if you can suggest a bound, and your friend can suggest another bound, and I can suggest another bound, and so on. Now, out of all these lower bounds, whichever is the greatest, then you say that the function cannot be lower than this, and that is infimum. But can the function be equal to that? That is there any value of x for which the function has its value equal to that? Then an infimum is a minimum also. So for minimum, there has to be a value of the point in the domain where that value is attained. For an infimum, a never never kind of limit is also fine. Similarly, between maximum and supremum. Okay. Now, note the different situations around points which attract your attention here. In this schematic graph of a function fx, okay, these are the points which may look having something to show. Point A, point x1, x2, x3, x4, x5, x6, b. A and b are the endpoints of the domain. Okay. So here you can see that point x1, point x4, and point b. These are minima. B is a minimum point from the one-sided condition. Okay. On the other side, the function does not exist. Similarly, A is a maximum point in similar situations. Okay. A is a maximum point. X2 is another maximum point, and X5 is another maximum point. Okay. Now, these 2 points, X3 and x6, are neither minimum points nor maximum points. Okay. So this is very obvious when you see the plot. Now, whatever we see in the plot, the conversion of that in the logic is basically what we are going to do in this course. Okay. Now, for this is what we get from definitions. Now, for differentiable functions, something more we can say, and easily we can say from derivatives. Okay. Then we say talk of optimality conditions. First of all, we define a point as a stationary point if there the first derivative vanishes. Okay. And that is a necessary condition for an extremum, minimum, or maximum for a differentiable function. If the function is differentiable, then at a at an extremum point, at a minimum or maximum, this has to be satisfied. Okay. So an extremum point of a differentiable function has to be a stationary point. If it is not differentiable, then it need not be. Okay. So based on that, you get the first order necessary condition. if fx has a minimum point at x star and it is differentiable, then the derivative is 0 at that point. Okay. Now, since it is necessary condition, that is all minima have to satisfy this. That is why if is on this side, then is on this side. There is something necessary to hold at extrema at the second order also, if the function is twice differentiable. Okay. If the function has a minimum point at x star and if it is twice differentiable, then the first condition is anyway here. Okay, nothing new. The second condition is that the second derivative has to be non-negative, positive or zero. Okay, for maximum it will be the other way around. Now, if this strict inequality holds here, then it is sufficient condition. Okay, so and that is why the sufficient condition is written with the if on the other side. If the function is twice differentiable at x star and first derivative is 0 and the second derivative is positive, then you can be sure that x star is a minimum point of the function if it is strict inequality. Okay. Now there is a little gap between the necessary condition and the sufficient condition. If the second order derivative happens to be 0, okay, so then you are not sure. And for first order, for single variable functions, the analysis into higher derivatives is not very difficult if the function is differentiable up to those higher orders. Okay. So, and as long as the derivatives exist, we can work out a Taylor series around the point x star. And the first term of the Taylor series fx star we bring on this side and then see the difference. Function value at a neighboring point minus function value at the current point. So from Taylor series, we get this. And this series immediately makes clear why we have the first order and second order necessary and sufficient conditions. First of all, if this derivative is not 0, then depending upon the sign of epsilon, whether we take the other point on this side or that side, this will become positive or negative. Okay, whatever is the sign of f prime. Okay, if it is not 0, then it is either positive or negative. So if it is positive, then for positive epsilon, it will be product is positive. If it is negative, then for positive epsilon, it is negative. And on the other side, it will be of the other sign. That means depending on the sign of epsilon, this term will be of the opposite signs. And for sufficiently small epsilon, this term will dominate all the other terms. Therefore, the entire right hand side will sway positive, negative according to the sign of epsilon, as long as this is not 0. That is why for x star to be a minimum point, a necessary condition is that this term should not play a role in deciding the sign of the right hand side. Okay, so this is 0. So this is necessary. So this is 0. This is gone. Once this is gone, this term will dominate the series for sufficiently small epsilon. And it can dominate only if it is non-zero. F double prime is non-zero, right? So if f double prime is positive, then right side will be positive because epsilon square is anyway positive. And in that case, all other points are above the current point. And so the current point is a minimum point. On the other side, if it is negative, then similarly we'll get a maximum point. And the gap is if this is also 0. So this is 0, this is 0. Then what? Then we try to resolve from here as long as this is not 0. Okay. And again, this is odd power. So it will be left, right, positive, negative, depending upon the sign of epsilon. That is why you see that the first non-zero derivative that you get, if that is of odd order, then it is neither a minimum point nor a maximum point. From one side it comes down and the other side also it continues to go down. So the current point is not minimum or maximum. Okay. On the other hand, if the first non-zero derivative is of even order, then the corresponding even power will not play a role in the deciding the sign, and the sign of the derivative will decide it. Okay, so that is here. The first positive or negative derivative being an even order, being of an even order, characterizes a minimum or maximum point. Positive, minimum, negative, maximum. The first non-zero derivative being of an odd order, whether positive or negative, it will not be a minimum or maximum. It will come like this and go like this, or come like this and go like this. Okay. So that point is actually a point of inflection, which the point need not be stationary for that matter. Okay. So even if first derivative is not zero, you can have points of inflection. But even if first derivative is zero, point of inflection can come in which the second derivative is also zero and an odd derivative appears as the first non-zero derivative. Okay, so this higher order analysis can be done very easily for single variable functions, and in high school you have been taught also. Okay, now we continue and discuss a few small things about the solution process, which we will continue to study afterwards. For single variable optimization, one important thing is bracketing, because it is possible for single variable optimization. For multivariate optimization, it is not possible. Okay, so bracketing is the identification of an interval in which you know of the existence of at least one minimum even before finding it. Okay, the condition for a bracket is for 3 points, 3 values x1, x2, x3 continuously increasing. If the middle one has function value lower than on both sides, then high, low, high. Okay, that means between these two highs, whatever low we have, if not that, then some other point nearby may be minimum. This is certainly lower than the two extremes. Okay, so this is called a bracket. In that case, x1, you say x1 to x3 is the bracket. In between this, there must be a minimum point. It may not be x2 itself, maybe somewhere on this side or that side. Okay, and this we say from continuity, because you see the continuity of the function we are assuming throughout. Differentiability may or may not be there. The function may or may not be differentiable. But continuity is something which we are assuming all the time. Okay. So from continuity, you can say that from high to low to high, since this is a pattern, then somewhere it has gone to a minimum. Okay. Because it cannot go deep into a pit of unfathomable depth and then suddenly rise somewhere without continuity. So continuity is something which we are accepting and assuming all throughout. Because if the function is not even continuous, then actually you cannot do a systematic optimization. Okay. So all algorithms actually rely on continuity. Now, how to get such a pattern? Very easy, almost common sense. Start at some initial value, evaluate it, and evaluate a little away. Okay. If that a little away function value turns out to be lower, then go further ahead, further ahead, further ahead, and so on. On the other hand, if this turns out to be higher, then don't go on that side, come on the other side. Okay, x naught minus delta, x naught minus 2 delta, and so on. So in any case, move along the decreasing direction of the function and go on moving till you find a situation when the function starts increasing again, and there you have your bracket. Okay, now do not keep this delta too small, because then you will spend a lifetime in doing this bracketing. Okay, so once you do this, in either case you get a bracket when the function decreasing 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 starts increasing again, then the immediately preceding, the lower one, and then the next higher one, that gives you a bracket. Once you have that, you have the surety that in between this there must be a minimum point, and then you try to find that out a little precisely. Okay, now at this point I should point out one important thing in which many students confuse. Okay, the bracketing process of root finding and bracketing process of optimization are different. In the case of root finding, when you want to solve an equation, you say on this side it is negative, on that side it is positive. There also, from continuity, you say that in between there must be a zero. That is for root finding, where you are looking for zero. Okay. Here, you do not look for zero, you look for a minimum. And that is why negative positive doesn't help. High, low, high is what you are looking for. Okay. So I am particularly mentioning it because in many years I have found the many students make a big mistake at the first step of the problem in exams. Okay, because based on root finding idea, they get negative positive and get a bracket which is not a bracket at all, and then the rest of the algorithm goes haywire. So don't do that. So in optimization, you are looking for high, low, high. For root finding, you may look for negative positive. Okay, so here it is the middle, lower, both sides higher. That is the pattern you are looking for a bracket. Okay, so that's it. Now this is a simple way to bracket a solution. There may be modifications, more sophistications, but doesn't matter actually. It's not of great use, any sophistication here. Now, what is the role of constraints in single variable optimization? It's not much. Why? Let us see why. First of all, if you have an equality constraint for a single variable problem, then what happens? Not much remains. A continuous optimization problem does not remain, because if the feasible solutions have to satisfy an equality constraint, which is an equation, then you typically expect one solution or a multiple number of solutions, not continuous infinite solutions for this kind of an equation. So an equality constraint for a single variable would typically limit the feasible domain to a set of discrete values, the roots of hx. And you do not have much of a continuous, continuous optimization problem. Okay. Now, if this function has 10,000 roots, then it is a problem enough, but it is a combinatorial problem, not the kind of problems that we are talking about. Now, in single variable problems, univariate problems, the common kind of constraints that we have are basically bounds. You may say that x is in the interval from lower to upper. Okay, that is possible. Even in the bracketing, we were actually trying to impose two such values. Okay, now both of these are inequality constraints. Okay, trivial inequality constraints, bound constraints. Now, a general inequality constraint like this may be there for a single variable optimization problem. But even here, if you try to really analyze then you will find that a single inequality constraint like this can give rise to a few bound constraints like this. For example, if suppose gx has roots x1, x2, x3, x4, where gx is 0, and across every root, suppose it changes its sign. Not necessary, but just if that is how it is operating, then what will happen? Suppose below x1, g is negative. Okay, then there it is valid, it is feasible. So from minus infinity to x1, it will be feasible domain. And then after x1, g is positive, so x1 to x2 is not feasible because it will not satisfy the constraint. Then again x2 to x3 will be feasible and so on. If gx changes sign across every root. Otherwise, you can work out the situation. If gx starts with positive, that is infeasible, then this will not be feasible. The other ones will be feasible like this. Okay? So eventually, even an inequality constraint will basically break down to a few intervals for you, either this interval or that interval or that interval, something like this only. So more than this complication, you will not get for single variable optimization problems if the problem remains in continuous optimization regime. Okay. Now, this is something very simple, first of all, and many methods for their own way of operation work with a finite interval. That is like exploring a finite interval, which is the you know region of our interest. We are not eager to find a solution somewhere. We are eager to find a solution in this interval. So an interval is something with which many methods operate as a sort of way of operation. So that is why for single variable optimization, we do not separately study constraint optimization. Single variable optimization, whether constrained or unconstrained, it doesn't matter much because the role of constraint is very limited. Okay. Now, in all kinds of optimization problems, single variable, multivariable, whatever, constraints are often external, that is driven by purpose. That is, if it is a design problem, then you say that within this region range of the variable values, we are looking for a solution. Okay. Or in other kinds of problems also similar external constraints come. But or sometimes for the convenience of the solution method, we impose certain bounds or constraints. Okay. For example, through bracketing. But then there are situations where the objective function itself gives rise to certain constraints of its own, some intrinsic constraints. For example, suppose the objective function is something like this. This kind of a situation can happen in multiple variate optimization also, where x has several variables. That there also it can happen. Okay. So suppose the objective function has a term like this. Then this will make sense in real variables. Okay. Only if this thing p of x inside the parenthesis happens to be in -1 to +1. Okay. Otherwise, sine inverse will not be defined. So the objective function cannot be defined. Forget about the point being feasible or infeasible. So some constraints come, you know, in package deal with the objective function itself. Okay. So the difficulty that may arise out of this kind of a function is that you cannot evaluate the function there and do a few things and then decide that it is an infeasible point. You cannot even evaluate the function there. An attempt to evaluate the function there itself will throw out your program. Okay, so your program will crash. So you have to take extra care to handle this kind of constraints. You should never attempt to evaluate the function at that point. There are other situations where you could evaluate the function, but the situation of the problem dictate that some constraints come with the function itself. For example, think of the objective function involving a convex combination. We have seen convex combination earlier in the discussion of convexity with the design variables xi as coefficients, x1, x2, x3, x4, etc. are the coefficients of the convex combination. Then these constraints appear as part of the description of the objective function. Okay, so these constraints you cannot do away. Each of the coefficients has to be non-negative and their sum has to be 1. Okay, so that is the condition of convex combination. So such situations arise and you have to recognize them. Okay, now let me summarize whatever we have got till now. From the definition, we found that no better solution in the immediate neighborhood means the current point is an optimal point. This is the first thing in definition. Optimality conditions help to validate a candidate solution. If somebody proposes a solution, you can quickly check whether it has any hope of being a minimum point, even though finding it may be difficult. Okay. For single variable problems, even in higher order, validation can be done. If up to second order, the decision is not conclusive. Bracketing is something which is very useful step, which you should typically do prior to the solution of the optimization problem. For single variable problem, you can do it, and to the extent possible, you should. In the next lectures, we will discuss methods to solve optimization problems of single variables. And the first one, immediately, we will discuss methods which use the concept of derivatives, derivative-based methods. Not necessarily that they use the derivative itself, but the idea of derivative is used here. Okay, so that is what we do in the next lecture. Thank you.